Okay, today we're going to be starting 3.2, properties of functions and some composite functions. A lot of these features you'll be pretty familiar with. First one is the concept of a y-intercept. That is where the graph is going to cross the y-axis. Of course, the x coordinate would have to be 0. And then we have our x-intercepts here, and that is where the graph would be crossing the x-axis. And here you would have the y-coordinate be 0. Can a function have more than one y-intercept? And the answer to that is no. If there's your y-axis, if we were to cross more than once, what would happen is we would fail the vertical line test. Can a function have more than one x-intercept? Here's an example right over here. It absolutely can. It can have multiple x-intercepts because that does not prevent it from passing the vertical line test. We also have even and odd functions. This might be a new concept to some of you. The way we want to talk about our even and odds here, I apologize, I'm messing up with the actual board here, but if I'm looking for an even function, I have my original function of f of x. What I then want to do is find f of negative x. If that works, that means that the function is even. Another way to kind of look at it graphically, it will be symmetric to the y-axis. So the first thing we do, we test for the even function. If that does not work, we kind of want to see if we can test for an odd function here. Then we're going to take what we found, this f of negative x here, and we're going to negate it. If that works out, then we have an odd function. Graphically, it is symmetric with respect to the origin. So for example, to get to the origin, I have to go up 1, over 1, over 1, up 1. I'm perfectly symmetric to the origin there. So let's just kind of look at this graphically. I want to determine whether these functions are even, odd, or neither. So I'm looking at this one. I can see that I am symmetric to the y-axis, so this function here would be considered even, which kind of makes sense. It is a parabola. We're looking at some kind of x squared situation there. If I'm looking at this function here, I want to see if it's even. It's definitely not symmetric to the y-axis. There's no matching point over here. I want to see, is it symmetric to the origin? So if I'm looking at this point here, if I went down 1, over 1, over 1, down to about the same spot, I'm not really matching up. So this one would be a neither. As far as C goes, also we are not symmetric to the y-axis because there's no matching point over here. However, if I go up and then I have to go over 1.5 and up, I am matching over here. So this one would be considered odd because it's symmetric through the origin. Looking at these graphically here, again, the first thing you want to do is find g of negative x. So the first thing I'm going to do is find g of negative x, which means I'm going to put a negative x in wherever I see an x squared. So that's going to be 2 times negative x squared minus 1. When you square a negative, it does become positive. Since this function is exactly the same as that one, what we have here is an even function. There's no reason to continue. So let's try with b. The first thing we do is we test for the even function. So h of negative x would be 2 times negative x cubed minus, and again we're going to put another negative x in there. Okay, so if you raise a negative to an odd power, it stays negative, so we're going to wind up with negative 2x cubed plus x. This function here is not matching the original one, so it's definitely not even. So now what we're going to do is we're going to take this function here that we just found and negate it. So we're going to find negative h of negative x, which means we're going to change the sign here and here. So it's going to get me 2x cubed minus x. Now these two guys match up, so this function is considered to be odd. Looking at C, the first step is to find f of negative x. And again, so we're going to go 2 times negative x cubed minus 3. That's going to get us negative 2x cubed minus 3. This function is not matching that one, so it's not even. Now you test negative f of negative x. So So we're going to change the signs here and here, getting me 2x cubed plus 3. This also is not matching the original function. So in this case, this would be considered neither. All right, so we're going to take a look at our graphs, and we want to kind of discuss certain features of them. We want to talk about local maximum and local minimums. Right here would be considered a local minimum because we're having a change in slope. Over here we're looking at a local maximum. You could have more than one local minimum. You could have more than one local maximum. So for example, this graph here is actually looking at 2. Eventually we'll start talking about absolute maximums and absolute minimums. This one has an absolute minimum here. This is the absolute lowest point on the graph. It has no absolute maximum because it's continuing up into positive infinity. All right, so A is just asking at which x values do we have a local maximum. So there's our local maximum, and our x value there is -1. What is the local maximum? When I'm asking for what is actually the local maximum, I'm asking for the y value. What is the output of that function? In this case, it is 3. At which x values does f have a local minimum? So we're looking here because there's a turn, and over here. So that would be at -2 and -1. What are the local minima, the y values that we're looking at? So the y value here is +1, and over here it is -1. We also want to talk about intervals of which the function is increasing. So increasing means we're looking at a positive slope. We're heading up the hill here. But I'm not asking for the y values. What intervals, anytime you hear that term, I'm looking for the x values. So what I'm looking at here is from -2 to -1 is where it is increasing. And we're going to put soft brackets around there because right here, right where it turns, it is considered to be flat. It's not going to be considered to be increasing. I'm going to then pick up again. Where does it start to head up again? Well, that is at 1, and that continues on to positive infinity. On what intervals is f decreasing? So we're coming across. Always think about coming from negative infinity. So we're starting at negative infinity as an x value, and we get right to -2. Again, not including that because, like I said, it's flat right there. Then it's increasing for a while. Then we pick up with another decreasing piece here. So then we're picking up at -1, and that continues on to 1. Okay, let's talk about average rate of change. So let's flip your papers over. This is called the difference quotient, and this is something that you will pick up again in calculus next year. So I want to know what is the average rate of change from 1 to 3 given this function here of 2x cubed plus 5. So the first thing you want to do is find f of 1. So I'm just going to plug 1 right in there, and when I do that, I get -7. Then I'm going to look for what is f of 3. So again, plugging 3 right in here, that turns out to be 59. Average rate of change is just think about it kind of like slope. It's the change of y over the change in x. So our two y values, our two output values here are 59 and negative, is it -7? No, this is a +7, excuse me there. So I'm going to say 59 minus 7. So I started with the 59. The x value coordinating with that is 3 minus 1. That's going to get us 52 over 2. So our average rate of change here winds up being 26. The next thing we're going to talk about here is composite functions. Kind of see this open circle in there. That's not meaning to multiply. If it's closed, it does mean multiply. This is saying f of g of x. Another way that might be notated is that g is the input for the function f. So let's just kind of take a look at these guys here. I have two functions. I have one that is f of x, which is just plain old 2x. G of x is 3x squared plus 1. I want to know what is f of g of 4. So we're going to take 4 and you go to the first function and plug it in there. So if I'm going to find g of 4, I'm going to put a 4 right in here. So g of 4 is going to be 49. So when I plug 4 right in where I see that x there, I get 49. Then I'm going to take the output here and use it as the input for f. So what is f of 49? And then we get 98. So f of g of 4 is equal to 98. All right, so let's look at b. Now we're looking at g of f of 2. So we're going to take the 2, go to the f function first, and put 2 in there. So f of 2 would get us 4. Now we're going to use this output as our input for g. So what's g of 4? Again, I put 4 in here, we get 49. So g of f of 4 is equal to 49. You can use the same function in this composite. So I'm going to say, what is f of 1? So f of 1, I put 1 right in here where I see that x, I get 2. Then using this output as the new input, what is f of 2? And then we get 4. So f of 1 is equal to 4. We can work with these as well. I'm going to start talking about domains again. We had that discussion in the last lesson. So I want to know what is f of g. So I'm going to take g, this function here, and replace it in wherever I see an x. So what we're going to have here is x squared plus 4 squared. So taking the entire function of g and replacing it right in here where we see that x. Remember to FOIL this out. We're going to get x to the 4th power plus 8x squared plus 16. So there's our composite there. Talking about domain, we do not have any denominators and we do not have any radicals. So our domain here is going to be negative infinity to positive infinity. Example B is just having us go in the opposite direction. We're going to take function f and now replace it everywhere we see an x in g. So I'm going to take this x squared, I'm going to replace it right here. So I'm going to have x squared squared plus 4, and we're going to get x to the 4th power plus 4. Again, there are no denominators, there's no radicals, so our domain is negative infinity to positive infinity. If I look at problem C, f of x, so I'm going to take x squared, this entire function, and replace it right in for x. So what we're going to get is x squared squared, which is going to get us x to the 4th power. Again, we have no domain issues. There's no denominators, no radicals. So we're looking at negative infinity to positive infinity. And the last one here, g of x. So I'm going to take x squared plus 4 and replace it right in there in that x squared. So I'm going to have x squared plus 4 squared, and still that plus 4 on the end. That's going to get us x to the 4th plus 8x squared plus 16 plus 4. And then combining up these like terms here, x to the 4th, 8x squared plus 20. Same domain, again, still not having to deal with any kind of denominator or any kind of radical. All right, moving on to example 8, finding the domain of f of g. So I want to find f of g of x. F is defined as 3 over x minus 1. G is defined as 2 over x. So I'm going to take g, 2 over x, and I'm going to replace that right in there where I see an x. So let's just find the function first. I'm looking at 3 over 2 over x minus 1. I do want to simplify this up, so I'm going to multiply by 1 equivalent of x over x to get rid of this denominator here. We do not want fractions inside of fractions. There's nothing to cancel out in the numerator, so we get 3x. Here the 2 x's will cancel, leaving us with 2. Then we still need to multiply this the second term of getting x over here. So this is our composite function right here. Now let's talk about domains. First you want to look at the 2 original functions. For f of x, x cannot be 1 because it would drive that denominator to 0. We would never be able to put them together in the first place. I take that back. So we're looking at, you want to look at the, sorry guys, you want to look at the first function, g of x. What x cannot be there is 0. It's irrelevant here. I could put 0 in here and still get -1. I could use, as before I was saying, and this is where the mistake came, if I put 1, if I restrict 1, it's fine to put 1 here. We're going to get a value of 2, and then when I put 2 in here, it does not drive that denominator to 0. So you want to look at the initial function here of g of x. Then we want to look at what is the combination here. So when I'm looking at our composite, what x cannot be over here is 2. So we cannot be 0. So x cannot be 0, and x cannot be 2. So what our domain is going to be is -infinity to 0, union with 0 to 2, and then picking up again at 2 to infinity. All right, so let's look at a couple of these here. We'll go through them. That will be the end of our lesson here. Now I'm defining f of x as 2x squared, g of x is 4 over x minus 2. I want to know what is f of g of x, so we're going to put all of g of x into here. So that's going to get us, let's see, 2 times 4 over x minus 2 squared. So we're going to square what's inside there first. We're going to have 2 times 16 over, I think I'm going to leave that as, I like to leave the denominators kind of in that factored form. And then multiplying in here, we're going to get 32 over x minus 2 squared. The reason I want to leave this in a factored form, it's easier to see what's going to drive it to 0. So I look at my original function here as far as domain. X cannot be 2. And then when I look at my composite function over here as well, x also, the only restriction, it would be the same one that we have here is 2. So our domain is going to be from -infinity to 2, picking up on the other side of 2 and heading towards positive infinity. Okay, this one here, now we're going to take f of x, and we're going to replace that where we see an x and g of x. So that's going to get us 4 over 2x squared minus 2. I really can't do any simplifying of that, so that's what the composite looks at. We want to look at the original function. So if I look at f of x, there's no denominators, there's no radicals, so there's no restriction on the domain there. Then I hop over to my composite function. What is going to make that drive to 0 if x is positive 1 or -1? So we can not have either of those there. So we're looking at x cannot be 1 and it cannot be -1. So our domain is going to be -infinity to -1, picking up on the other side of -1 to 1, and then the other side of 1 to infinity. Looking at c, now we're looking at f of x. So I'm going to take 2x squared and replace it exactly where I see that x. So it's going to be 2 times 2x squared squared. We're going to square what's inside here first. So that is going to get us 2 times 4x to the 4th. And then multiplying that 2 through, we get 8x to the 4th power. If I look at f of x to begin with, that was our original function. There's no domain restriction there. When I look at the composite, again, we have no denominators, we have no radicals, so no domain restrictions happening, and our domain becomes -infinity to positive infinity. Okay, these ones here, now I'm not looking for any kind of domain restrictions on these. I just want to evaluate what's f of g of 5. If I put 5 in here, so I find g of 5, and that is going to be 4/3. Once I know what 4/3 is, I take the output from g of x and use it as the input for f of x. So what's f of 4/3? Applying that inside the x value over here. So that's going to get us 2 times 4/3 squared, which is going to be 2 times 16 over 9, and eventually we're going to land at 32 over 9. There's no reason to do anything with that fraction, just let it be. G of f of 2, so if I look up f of 2, I put 2 right over here where I see that x, we're going to get 8. Then you take this output, it becomes the new input for g. So g of 8 would be 4 over 8 minus 2, which would be 4 over 6, which would reduce to 2/3. And the last problem here is just asking for f of negative 2. So I look at what is f of negative 2. When I put that into the x value here, negative 2 squared is 4 times 2 would get us 8. Then I'm going to evaluate what is f of 8. Again, the output becomes the new input. And we wind up with 2 times 8 squared, and we wind up with a total of 128. And that concludes our lesson on properties and composite.